Hello everyone, I am Akshat Dhiman, a master's student at Northeastern University in cloud computing concentration. Over the past few days, me and my teammates built Travel Intelligence Platform, a B2B aviation analytics solution running entirely on AWS. The platform predicts flight delays using machine learning, surfaces operational insights from 3 million historical flight records, and ingests live flight data through a fully serverless pipeline. Let me walk you through what we have built. So every year, travelers and businesses lose billions of dollars due to unpredictable flight delays and suboptimal booking decisions. The data needed to solve this problem is publicly available, but it is scattered, raw, and not actionable for end users. Travel agencies don't know which routes are most prone to delays. Corporate travel managers don't know the best time to book the flights. Insurance providers price their products without granular route level risk data. So we designed our platform to answer four key questions every traveler should know before booking. So, which routes are most prone to delays? What's the best time to of the day to book? Which airline are most reliable? How the disruptions like COVID, weather, ATC cascade through the network. Now let me show you what we have built. So now let me walk you through the system architecture. It is organized into five clean layers. Zone 1 is data source. We are pulling the historical data from Kaggle BTS dataset. It is a 3 million flight records spanning from 2019 to 2023 and it formatted in CSV format. For live data, we are using the Aviationstack REST API, which are Lambda polls in every 12 hours. For zone 2, which is ingestion layer, historical data was bulk loaded once through AWS CloudShell, and live data flows through an AWS Lambda function written in Python. The Lambda is triggered by an EventBridge, and it reads the API key securely from AWS Secrets Manager and logs the execution to CloudWatch with a retention period of 7 days. Layer 3 is our S3 data lake. Three buckets are in total, one for raw flight data, one for processed data, and one for machine learning modules. Everything is hived and partitioned by a 4 year for frequency efficiency, which you can see here. Layer 4 is query and machine learning layer. Amazon Athena gives us serverless SQL directly on top of S3. Our database, Travel Intel, contains one external table and five analytical views handling cleaning, feature engineering, and business specific analytics. The random forest classifier we train connects directly to this layer, which I can show you here. So these are our five views. Zone 5 is the consumer layer, a six-tab Streamlit dashboard for analytics, a stub REST API designed for future B2B integration, and an SES email alerting system documented for production rollout. The entire platform runs for under $1 per month on free AWS tier. Of the data pipeline. As mentioned earlier, we are pulling data from two sources. One is historical data and one is live data. So for historical data, we are pulling it from Kaggle and it is partitioned in by year. So each year has its own CSV file. This Hive style partition means that Athena scans only the data which we actually need and keeping the cost at fractions of cents. So talking about live data, it has been partitioned more granularly, in the format of year, month, day, and hour, and it is stored in a JSON format. The pipeline has been executing it from 9th May, and there is no manual intervention required for it. So this is our Lambda function, which that handles the ingestion. It runs twice daily, fetches 100 flight per call, and writes them into S3 with proper metadata. Average execution time is about 1.4 seconds, and it uses only 1 or 3 megabytes of memory. This is our EventBridge where we have scheduled the cron job. So it runs in every 12 hours, and here are the next 10 triggers, which will run up till May 17th. So once the data lands from S3, we query it through Amazon Athena. Our travel intel database has one external table, flights, point plus the five analytic views that we built here. The most important is flights clean. It handles cleaning and feature engineering at query time, extracting departure hour, day of week, route ID, and delay categories. This is a modern ELT pattern that lets us iterate faster than in traditional ETL Lambda word. So let me run a real query against the platform. This pulls hourly pattern view, aggregated delay statistics for all 12 hours of the day across 3 million records. So if you look at the pattern, the flights between 5 and 11 a.m. have delay rates around 7%. Late at evening, the flight jumps from 25% or more, and the query scanned around 580 megabytes and ran in under 3 seconds, costing roughly one third of a cent. This is the kind of insights corporate travel managers will pay for real money. Now, let me show you how we turn this data into a predictive model. For random delay prediction model, we chose a random forest classifier from scikit-learn. Random forest gives us interpretable feature importance scores, exactly what customers need to trust the predictions. We trained on 240,000 stratified sample drawn from over 3 million records of the dataset. After one hunt encoding airline codes, origin, and destination airports, we ended up with 85 features. Model achieved an AUC of 0.6673, which sits firmly at the published baseline for flight delay prediction. The flight delays have a substantial irreducible randomness, like weather, mechanical issues, air traffic control. No model can predict them perfectly. Academic papers in this space typically report AUC value between 0.65 to 0.75. So we are solid in that range. The most important and interesting finding from the model is feature importance. Departure R alone explains a 48.5% of all predictable variance. Month, distance travel, specific carriers like Southwest and JetBlue follows. This confirms what the dashboard already suggests. When you fly, matters dramatically more than which airline or which airport. So now let me run the dashboard on localhost and see like what the end user will be seeing on the dashboard. So the dashboard runs on the local host and the KPI is running right now. And once it loads, we'll be able to see the data populated on it. So right now we can see 2.9 million flights has been analyzed with a delay rate of 17.56% and average departure delay is 10.1 minute. And it has calculated 7,771 unique routes. So the delay patterns by hour of the day. In this chart, each bar represents 1 hour of the day. The morning flights has been colored in green with a 25% of with the 10% delay rates, and the orange one are the afternoon hours or the evening hours, and this has a 25% of delay rate. So from the visualization, we can clearly see that the we should book a morning flight, not the evening ones, because they have a 25% of delay rate. So let's move to worst performing routes. This is under the route analysis. So we surface the top 15 worst performing routes ranked by delay rate. Travel agencies can use this directly to set traveler expectations or recommend alternate bookings. In the airline tab, we can see the airline performance. Users can filter by year to see how each airline carrier performed over time. The 2023 view shows clearly winners and losers in the operational reliability. Also, like you can check for every year, it will run the query again for each year. So moving the COVID impact, I'll let this query finish. So now moving to COVID-19 aviation impact. This is one of our favorite findings. Notice that 2022 and 2023, after the pandemic, actually had higher delay rates more than the 2020 and 2021. Airline aggressively scheduled flights during the recovery period without sufficient crew and aircraft buffer, which created operation fragility. And now let's go move to the delay prediction. Our real-time machine learning delay prediction this lets us analyze or predict the risk of delay for Southwest flight from an origin airport to a destination airport. So let's just run the departure hour of the day, like for which hour you want to book the flight, and the distance in miles. Day of the week, like one is Monday, two is Tuesday, three is Wednesday, and going forward. So this is the origin airport, and this is a destination airport. And we also have to select the month of the year. So we'll predict the delay risk. So as you can see, it has the delay probability of 48.9%, and it also shows that it has a high delay risk. Now let's move to the live pulse. So this shows our most recent live data snapshots from the live data which we have ingested from Aviationstack. The pipeline has collected 9 snapshots since 9th May, and the latest contains around 100 flights from around the world. The pie chart on the left shows the breakdown of flight statuses. The bar chart on the right shows the top destination currently being tracked. This entire dashboard is powered by Athena Views and ML model. To summarize what our team has built, it is a B2B aviation analytics platform on AWS, processing 3 million historical records plus live API data through a fully serverless architecture. The platform runs under $1 per month, demonstrating strong unit economics. We documented every component end to end: architecture, code, business case, and operational decisions. The full repository is publicly available on GitHub, and this is the README file which will walk you through everything we showed you in the video, along with a complete future work roadmap covering REST API deployment, real-time SES alerting, and geopolitical disruptions tackling. So, huge thanks to Maharshi, Karthik, Janam, and Kirti for collaborating throughout. Feel free to clone the repo and run it yourself. Each ingestion file analytics, which are like the Athena queries which we ran, and ML models, and dashboard code with API handler which you can locally run as it we have feed it in a sample data which will show you a prediction in the through this API call. And infrastructure is also like we have added it into a architecture file, and the documents for business case and also along with the screenshots has been added to this GitHub repository. Thank you for watching.